Some components in a car are critically important. If one or more of these critically important components fails, the car will not run. Let's imagine there are only 10 such critical components in a car. If each critical component has a 95% probability of working properly, calculate the probability of the car not running, so probability of the car not running due to a failure of one or more of these critical components. All right, so I'm going to write a probability statement for this. It's the probability the car essentially does not run. So car does not run. And the reason why it wouldn't run is because there's some failure of one or more of the critical components necessary for the car to run. So let's look at this phrase, one or more. We could say this another way, which could be advantageous to us. So one or more means either one or two or three fail, so on and so forth, all the way up to the possibility that 10 fail, right? And so there are many cases here, and that means many probabilities would have to be calculated to figure this out. And you'd have to add them all together, because these ors mean you would have to sum all those cases together, all the individual probabilities, to get the final total answer for all the ways that the car wouldn't run based on some of these or all of these components failing. That's hard, so we want to avoid doing that if we can. It turns out we can avoid it in this case because we have this nice complement which allows us to get the probability using a roundabout method. And that roundabout method is the probability of at least one. And this is going to be equal to 1 minus the probability of none. So this is a complementary relationship, and it makes sense here if you think about it. The only way you don't have at least one of something is if you have none of it, right? Because if you have one of it, you have at least one, right? So one or more, right, is at least one. So that's a complementary idea that applies in all situations. And we can make it work here for us by just filling in the language of the problem. So again, one or more is really the same as the idea of at least one, right? At least one means one or more. And at least one or more of these components fail, it says, is what we're looking for. So at least one failure. And then I can just add the same terminology over on this other side here to complete this statement. So it would be 1 minus the probability that none fail, right? So if I work out this probability, which is actually much easier because there's only one way that none of them fail, if I work that out, then I can get the answer to the question I really want, which is the probability that at least one of them fail. All right, so why is it easier to do the probability that none fail? Well, think about it. The only way that none of them fail is if they all work. So it'll be 1 minus the probability that they all work, right? And that probability is going to be calculated by creating 10 little spaces here. Now, I'm not going to put all 10, but you get the idea. There'll be 10 spaces, and they will represent each component. So this is the first component, right? This is the second component. The third, right? So on and so forth, all the way to the 10th component. And we want each of them to work, because if they all work, then none of them will fail. And then we can subtract that answer from 1, and we'll be left with the probability that at least one of them fails. All right, so let's figure that out. What's the probability that the first component doesn't fail, right? Doesn't fail. What's the probability that the first component doesn't fail? Well, according to the problem, 95% of the time, right? 95% of the time, the components will work properly. So that means the probability that this first component works is 95%. Now we're going to assume that these operate independent of one another, and the probability, therefore, that the second component doesn't fail is also going to be 95%, right? So remember, 95% chance that it works, that's the same as it not failing, and same probability for the third component, and so on and so forth. So we'll be able to assume that each of these has a 95% chance of working, which means that the answer to my question is going to basically be 1 minus 0.95 to the 10th power. Why 10? Because there are 10 components here. And if we do that calculation, we should have the answer to the probability that at least one fails. All right, so I have my calculator open here. I'm going to do 1 minus 0.95 to the 10th power to see what that gives us. So we end up with a calculation of 0.401. So this final answer then is 0.401 or 0.401, which is the same as saying 40.1% of the time the car will not run, right? It will not run because there'll be at least one failure of a critical component. So if there's 10 such critical components and they only work 95% of the time, our car is going to break down a lot.
Hi, I'm Dane McGuckin. I created a video website called statsprofessor.com. It's designed to help stats students like yourself. In fact, I created it for my own university students who are taking my elementary statistics courses. The website is free. You don't have to register or anything. You just go there and find the videos you need. Everything is organized by chapter and subsection, so it's like navigating your textbook, nice and easy to find everything you want. While YouTube is a wonderful place to find videos to help you learn almost anything, there's a lot of searching involved and you're not always sure what you're going to get. So check out my website, subscribe to my channel, and see if you like my instruction. If you do, the website's a great place to get the same consistent quality help every time you need it. Thanks for watching.